For problem 3-5.1, as I recall it, you had an f of x equal to 2x for x greater than 0, less than 1, and 0 else. It had something that says, first it says fy of y. For f of y, they say it's uniformly distributed between -1 and 1. So that would mean it's got a value of 1/2 from -1 greater than y, less than 1. And we could graph that, but it's pretty obvious, and 0 else. It looks like this, just from -1 to 1, its value is 1/2, and this would be fy. For this one, well, that's kind of straightforward. It's just going to be a value of 2 at x equal 1, and then 0 else. So now they come up with a variable, and they say let z be equal to, and this is 2y plus x. This is the trick in this one I'm about to show you. All right, here's the problem. All the problems in this section that are set up to be done efficiently assume that x and y, or whatever the two variables are independent. One is not dependent on the other. You can't do it if they are. That's the next section we're doing. So if they're independent, the way I need to make this turn into a convolution problem is have this appear as z is equal to some function plus some other function, and get rid of all the coefficients like 2 and 5 and 6. So I'm going to say z is actually equal to g plus x, and here I'm going to say g is equal to 2y. The reason I'm doing that is now I've got just two basic variables like x and y. Now it's g and x. Now here, remember, if y is uniformly distributed from -1 to 1, because g is 2y, my f of g here will be equal to, and it's going to be, instead of 1/2, it's going to be 1/4, and this is going to be from g, or I should say little g, greater than -2, less than 2, and 0 else. And I'll even plot it. So now the uniform density is the key to these. So here it's 2, and this is 0, and this would be g. Now, both of these two functions, we can go ahead and prove that it'll fall into a convolution type form if I wanted to. Maybe I'll do it real quick, but you don't need to write this down, just follow me. Remember, if I want f of random variable z less than the actual value of z, that's the same thing. This would be a distribution function too, as f of quantity x plus g less than z. Z here is a constant. And if you look at that, this f of x plus g, or capital G, sorry, less than z, well, it's going to be a double integral. And here, you're going to have an integral. It won't matter which one we do first. We can go f of g and take it, and this is going to be as a function of g, dg. And it's going to go from 0, or really from technically -infinity to, even though a lot of that integration is going to be 0, to the value given here. So g would be equal to z minus x, and then it would be an f of x from -infinity, and x would go to +infinity and be dx. Now, I've written that down there only because this is the distribution function, and the way you get the density function, f of z, is to take a derivative of capital F of this one, x plus g less than z with respect to z. When we take a derivative of this part right here, the dx integration doesn't change, and I'm going to write it down here. That means this is in the book, by the way, in this section, so you don't have to write this down. When I take a derivative, I still get the integral from -infinity to infinity there, But then here I get the derivative of the upper limit with respect to z, which is just 1. And then it's times, then what you have to do is take this argument and replace g with z minus x. And this is going to be times f of z minus x dx. Now, the reason I did that, and the only reason I did that, that is the exact formula for the convolution of two functions. You're used to seeing convolution as an integral from minus infinity to infinity of a dummy variable, f of x of, say, tau. And then it's going to be f, and this would be f of g right here, f of g, and this would be t minus tau d tau. Now, what used to be t when you took signals and systems is really going to be z for us. But this is the convolution integral. Do you agree with that, everyone? And the d tau, remember, when you integrate d tau, you get rid of it. So we call it a dummy variable. Having said all that, we realize that this is just the convolution of the two functions. And you can replace x with anything, and you can, it doesn't matter because you're going to integrate it out. Do you see that right there?
Yeah.
All right, it doesn't matter. So I can say if it's the convolution of these two functions, this function right here and this function right here, I'm going to flip the page. Now what I'm going to say is because this is the convolution integral, I'm going to take these two functions and convolve them on the next page. So here's the two functions I'm convolving. And I'm going to put them in terms of a dummy variable. And it doesn't matter if it's x or it's tau, but I'll use x. So here, this has a height of 2. This is 1, and we'll call this x. And this is my f of x, right? Now, I'm not going to flip and shift that one. I'm going to flip the other one. Remember, the other one had an extent from -2 to +2. When I flip it, it looks the same. Remember, you know how I'm talking about, instead of showing you g of minus x, I'm going to take it and flip it. But here's what actually happens, and I'm going to just try to draw this well. This is going to be equal to my g of minus x just by itself. Now, actually, I can say, instead of that, I can do it this way. I can say g of z minus x. Do you remember that was the argument? All right, now this upper part right here, this is going to be z plus 2. The lower part is z minus 2. And this is x. Can you all follow me? It's still, this horizontal axis has x as its variation. Now, when I look at the definition of f of z, and I'll change something in a second, it's equal to the integral from minus infinity to infinity of f of x times g of z minus x dx. Now, I flipped it, and the upper limit is z plus 2, the lower limit is z minus 2, and you can see here, what I want to do to have the beginning of the overlap area, remember, we want this integration. Here's f of x. F of x exists from x equals 0 to 1. We want to take this thing and move it all the way down till it's just coming across the 0 point. So we can say if z is equal to -2, I'll put z greater than -2, but less than -1. Now, if you think about this whole rectangle, you think, I mean, that's basically the width. Now I've moved that window down to here. Can you see that? I mean, normally it would be this one, right? Now I've moved it down here for if z is -2, the upper limit here would be -2 plus 2 is 0. It's just starting to creep in. With me? And the height of this is 1/4, by the way. Because this is I should say, this is f of g of z minus x. It's the density function for f of g. That's what I should have said. So when I look at this part of the integral, f of z for this part would be equal to just the integration from 0 to the upper limit, z plus 2, of, and now I've got to take this 1/4 and I have to multiply, that's this function, by f of x. Well, f of x is just going to be equal to, that's just simply 2x, right? dx, with me?
Where did you get the bounds again? 0 to z
All right,
plus.
think about, just look here for a second. See the width of that?
Yes.
All right, that's at z equals 0. It goes from -2 to 2 at z equals 0.
Oh,
When z
okay.
is -2, the window's just starting to get in. It's all right. Then the overlapped area would be from 0 to z plus 2.
Okay.
All right.
You just plug it in.
Yeah, but you got to think about the limits on that. That goes from -2 to -1, right? And then when z is -1, the upper limit is 1, right? Minus
Yeah.
1. Then after that point, for the next 3 intervals, right? It's got just a constant area, or 2 intervals, I should say, constant area. So
The reason why
now,
I'm doing this is because of the f of x function that's 0 to 1.
that's right.
Okay.
So
Okay.
this is equal to, if you look at this, this is 1/2 times x dx. When I integrate 1/2 x dx, I get 1/4 x squared from 0 to this. So I get 1/4, right? And it's going to be z plus 2 squared. And he'll have that. It'll be 1/4, and it'll be z squared plus 2z plus 4. Do you have the solutions out? That's the beginning of the shark's fin. You got to take a look at, when does this lower bound right here, z minus 2, hit 0? It's when z is 2, right? Now you say, if I am from z equals -1 greater than z less than 2, that's the range where this window right here, Nick, watch this, you can help your friends. Now this whole window, remember the window that I'm showing you here for the f of g, z minus, that has a span of 4, right? Here, when you go from -2 to -1, there's still 3 units you go through. So you go through 1, 2, right? And actually this should be 0 to 1, I believe, because this is where it is at -2. That would be -1. Then we still have 2 units, -2. Sorry. When z minus 2 is equal to 0, z is 2. Actually, it is 2. My bad. So from here to here, now you're going to get f of z is a constant. And it's just this area right here times 1/4. Well, that area is 1, so it's just equal to 1/4. And that's going to be from z, from -1 to 2.
So you're moving the f of g.
This window right here is moving that way, right?
Yeah.
All right, so when z is -2, it's just here, right? It's right
Okay.
here. Now, when z is -1, now the entire triangle above is in the area of the integration, right?
Yeah.
When it goes up again from -2 to 0, all the triangle's still immersed, right?
Okay.
And when it goes to 2, it's still immersed.
Okay.
And the area would be the area of this, which is 1, it has to be, times the area of this, or times, sorry, the height is 1/4, right?
So when you're choosing where this is moving, you're trying to pick values. So when you say z is -2, then you're going to be at the 0, and then you're going to be all the way shifted left, where the right part of that function is at 0, which is the start of where.
That's right. Where the areas, where the actual horizontal axes overlap.
Yeah. And then you have to then pick, then you're picking the next lower bound to be -1, and then you're shifting over, and then your next is going to be z0, right, to shift over. When are you done shifting? How do you know when you're done shifting?
Well, when you finally have no overlapping area. So at z equals -2, do you agree that's what this lower window looks like, right?
Yeah.
All right, call it a curtain. Now the curtain's moving through, and there's more and more of this area that's being that's going to be involved in the integration, in this integration. Finally, when it goes to z equals -1, all this is going to be involved. It's going to be the height of the lower one, which is 1/4, times that area, which is just going to be 1/4.
Yeah.
Now, as that thing moves back from -1 to 0, still this curtain, you might say, is still over the region from 0 to 1.
Okay.
Then as it moves again, right?
Yeah.
It's still going to be over that, right?
Okay.
That's how you get that. So this.
Whoa, okay. You just encompassed all of it into one range.
Well, because
one, two, the whole thing is going to be covered.
Right. Anytime that there's going to be a form of the solution that is constant, whether it is, in this case, it's not really constant, it's a function of z, but it has the same initial form. You pick a z and I've got it for this range. You chunk that off. Now, what's about the next part? Now, look, now we have this, right? So now you're going to have, I'm going to put this just f of x again. I want to make sure you see this. This is versus x, has a height of 2. Now the curtain's moving, but now we're going to be, the lower bound is z -2 right here, right?
Yeah.
Now when z is greater than 2, think about it. When z is greater than 2, but less than 3, now what happens is, here's what this thing looks like. Okay. It's going to be, here it's z -2, here it's z -2. This is x going this way. Z minus 2. This is z +2, but the overlapped area is only going to go to 1. Follow me?
Yeah.
So you need this area times 1/4, right? Okay. You can do it several ways, all right? But the easy way is, maybe it's the easy way. Let's just integrate the function f of x from here to here. F of x is just 2x, right? From where it's non-zero. So now I can say my f of z for this part, and this is the answer, I'm pretty sure, is going to be equal to, well, I know I have a 1/4 multiplying that, so I have 1/4, and now I have the integral from the lower bound is z -2. I hope you can see this. And the upper bound is 1. The reason it's 1 is all this area is multiplied by 0.
Yeah.
So now I have 2x dx, and you can see what happens. I get 1/2, then I integrate this. So I get x squared over 2, so I get really 1/4. And then I have to evaluate x squared at 1. Well, x squared at 1 is 1. And then it's going to be minus the quantity z -2 quantity squared. Now, we'll do that in a second. What is this going to be? Well, that's simply 1/4, right? 1 minus, it's got to be minus z squared. Then you have -2 squared, it's 4, so it's -4. And then you're going to have plus 2z, right? Or 4z. Agreed? Here I have 1/4, and then I'm going to have, what is that? 3. You could just leave it like this if you want. 3, and it's going to be plus 2 or plus 4z, and it's minus z squared, and that's true for z between 2 and 3. And it has a total width of 5. It has to, because when you do convolution anything, you take the width of the first function, if they have finite duration, and add it to the width of the second. That has to be the duration of the convolved function.
Okay.
So if you plotted it, and it's in the book, it starts at -2, and it does like this, and it's going to go here and then down here. This is the shark fin. -2, -1, 0, 1, 2, then 3, and that's f of z. All right. Now, if you got that, and he asks the probability of z being greater than or less than anything, if you've got f of z, you're just going to integrate this function over the range that they're asking, right?
It would be the probability of 0, that z is greater than 0 and less than 1.
All right. Now look at this, guys. All right. This has a height, he didn't show it here, of 1/4. Yeah, I did. So this is 1/4. You see that?
Yeah.
All right. from 0 to 1. It's 1/4 times 1. It's 1/4.
Could you use Laplace for the one we just did too?
Sure. We had f of x is just equal to 2x u of x, right?
All right.
Well, actually, this is from, sorry. It's going to be u of x minus u of x plus, or x minus 1, right? It only is non-zero for 0 to 1. All right, so you need these two u of x functions. Do you find this turns it off, this turns it on? What about the other one? My f of, I call it f of g, right? Matter of fact, let's do just f of, I'm just going to call it f of y. And I'm just going to say for this one, it's going to be a value of 1/4, but it turns on at -2. So you have to have u of y plus 2 minus u of y minus 2, because that's the range that you have to, I could put a pulse function in there. Actually, Laplace transforms of pulse functions technically don't exist unless they're for all positive values of t, right? Or for the positive. And the thing is, this has values. Laplace, remember, Laplace transforms require that the function you're taking the transform of has the lower, I mean, the axis, the horizontal axis has to start at 0 or greater than 0. If it's less than that, technically you can't use a single-sided Laplace. You have to use a double-sided Laplace, and that's beyond what you know. Or you could use a Fourier transform, and we could do it with Fourier transforms too. Either one we can do this with, but it's a little tricky. And the reason is you see this has values for y negative. Now we could use a Fourier transform for this one. The problem is, here's where it gets ugly quick. When you do a Fourier transform for these things, to do partial fraction expansion, it becomes difficult. So there's some tricks to this. For this one, it's probably easier just to do the convolution. Actually, let me think about that. Let's see. This is a pulse function. And I could say fy of y is actually equal to 1/4 times the pulse function of with 4, and it would be centered at 0, so of y. Now, that would be a rect function where you're at, and here, normally a rect function has the argument like the horizontal axis, in this case, y, and it would be divided by the width, which would be 4, but this is the same thing. It's called a pulse function. And this would be f of x. And f of x here I could write as a pulse function. I'm not going to spend too much time on this next, but I'm just mentioning this. And this is 2x, and this would be a pulse function here of with 1, but it's centered at 1/2, so it's going to be x minus 1/2. Rect of t over tau is the same thing of a pulse function of tau of t. Now here's the problem. This function right there has a Fourier transform. So if I take, I wanted f of y of omega, for this one, it's going to be equal to tau, which is the width, and that's going to be the sinc function of, and now you're in the omega domain, omega tau over 2. This would be the Fourier transform of this function. Now, the Fourier transform of this function is a little tough because first you have to take the Fourier transform of the pulse function, and then you have to use the property if you take t times any function and you want to transform, it's the derivative of that function, of the transform of the function, and it's going to be times aj. It's a property. I really don't want to go that way for this one because you're going to get confused with some of the stuff, but it's a property in Fourier transforms. If you have f of t, and it goes to f of, or capital F of omega, then if I have t, f of t, that goes to, if you look at it, minus j times d omega of f of omega. Do you remember that at all? 3-5.5. This one, they say two functions. F of x is equal to 5e to the minus 5x u of x. And then they have, I call that of x, fy of y is 2 e to the minus 2x u of x. I think that's right, right? Or u of y, pardon me. U of y. All right. Now, both of these functions only exist for their arguments, the horizontal arguments, greater than 0. So you can use Laplace transforms for that. And I'm going to say that I know that f of z will be guaranteed, because they say z is equal to x plus y in the problem, and x and y are independent. Because of that, f of z is going to be f of x convolved with f of y. You agree? That's convolution. I don't like convolution. So anytime I can, I go into the Laplace domain, sometimes the Fourier, but Laplace is the way to go. So if I take this, I'm going to get my f of z of s equal to, and now it's multiplied, f of x of s times f of y of s, 5 e to the minus 5x u of x. That transforms, and the whole idea is e to the minus at u of t transforms as simply 1 plus a plus s. This will just be 5 over s plus 5. And likewise, if you think about the 2 e to the minus 2y u of y, simply becomes, and I'll put it here, that's going to transform as 2 over s plus 2. So now I know my f of z of s is just going to be this times this. So it's 5 over s plus 5. And then it's going to be 2 over s plus 2. That's partial fraction expansion, right? So that will be equal to a over the pole here, which is s plus 5, plus b over the pole here, which is s plus 2. How do I get a?
Multiply both sides by s plus 5.
Right. And what do you do then?
And you cover up
The s plus 5 and?
that s equal to 5. Negative
minus 5, right? So when s is minus 5, you find a is equal to 10, right? And remember, you multiply through by s plus 5. That one's gone, right? So minus 5 plus 2 is minus 3. So it's 10 over 3 with a minus sign. And b has to be the same magnitude, opposite sign, because these are two simple pole functions multiplied. And this will be 10 thirds, and that means my f of z of s is equal to, and I'll put the b first, so it's 10 over 3, right, over s plus 2, and that's going to be minus 10 over 3 over s plus 5. Now we go to the other domain, and what happens? Let's take it back to the original domain we came from. It's usually time if you're doing signals and systems. Here it's z. So fz of z is going to be equal to 10 thirds. And what's the inverse of 1 over s plus 2?
It's going to be e to the negative 2z.
Right. And it's all going to be times u of z. And then it's going to be what? Minus 10 thirds times
e to the minus 5z.
5z, and all times u of z. And that's it. And that is the answer. But that is much, much easier. You can do the convolution. I did it in class. But this is easier for this one. Now, the one I'll tell you will get you. Here, now this guy's a bit of a rat doing this. He says I got x of t is cosine of 100t plus some phase angle, and y of t is cosine 100t plus some phase angle. Forget the 100t, X it out, it doesn't matter. It appears in both. It isn't going to change a thing. It says it's distributed evenly from 0 to 2 pi. Go from minus pi to pi. Then they say, well, I have x of t and I have y of t. Now, technically, they both are moving at the same rate, 100t. So there's an angular skew that's the same rate in both of them. They say, well, if z of t is equal to some a cosine of omega t plus phi, solve for a. All right, now here's what they do. They don't show this to you, but I'm going to show you what they're doing. Cosine. And again, I'm going to make that 100t go to 0 of some phase angle. I think the first angle is theta. This angle, his last angle, is what? Phi. So it's a cosine of phi is equal to And then it's going to be cosine of theta plus cosine of psi. Now, the only thing I'm doing is showing you, here's his x, here's his y. He wants z equal to sum a times cosine omega t. So z is x plus y. When you're looking at this, call this the x-axis, call this the y-axis. When I have cosine of theta, that really is a value of 1, and the projection here would be cosine of theta. You with me?
Yeah.
Now, when I have cosine of phi, here, there would be an angle phi here, and the projection of this would be psi, cosine of psi. This is a trickier problem. You all with, I mean, can you follow me on that? I'm really trying to say that this has a length of 1. The angle here is psi right there. So if I look at that, this is the projection right here, right? I might need to write this a little neater. I'll try to do it here and show you. Now, it's equal to, oh boy. It's equal, here's A, and this would be A times the cosine of phi. You all follow me on that?
Right.
I probably should have bent that up. Well, the vertical distance would be A times the sine of phi. And if you look at this, the vertical distance here based on this and this, if I added them together, x and y. Here I got 1, this is cosine of theta. The height of that would be sine theta, or sine of theta. Then I'm adding to that this one, I'm going to go up higher, has a height 1. The distance in this direction is going to be cosine of psi, and the vertical distance here is going to be sine of psi. Finally, I know that this is my A, and if I take the projection of that, I get A times the cosine of the angle it makes, which is phi, is going to be equal to this, which is cosine of theta plus cosine of psi. Can you follow me on that? Now, look, the vertical one is also going to be a sine of theta and a sine of phi, or sine of psi, sorry. So if you look at this, this squared plus this squared has to be equal to a squared, and that's the key. A squared is equal to this squared, which is going to be cosine of theta plus cosine of phi, quantity squared, plus sine of theta plus sine of psi squared. Now you're going to get terms where you get cosine squared of theta, cosine squared of psi, but you get plus 2 cosine of theta, cosine of psi, and then you're going to get sine squared plus sine of theta squared plus sine of psi squared. At the end of the day, cosine squared plus sine squared equals 1. Take the horizontal dimension, square it, vertical dimension, square it. That's what I'm showing you right here. That has to be equal to the hypotenuse squared. That's a squared. When you square these terms, you're going to get a cosine squared theta, and you're going to get a sine squared theta. That's 1. You're also going to get a cosine psi squared and a sine squared psi. That's 1 as well. There's 2. Then you're going to get plus And you're going to get some crazy terms in here, but then this is solutions. I work these things. These are a little more difficult than usual. It took me a little time. He has some trig identities. I don't use those trig identities. I use others. I try to do things different way, but I want you to see this. All right, now he's going to get A. Now you'll notice after you do an identity with the terms, the sine cosine terms, you get this, because remember cosine A or cosine A minus B is cosine A, cosine B plus sine A, sine B. It's just one of these things. At the end of the day, when you mess with this, you get this. It's going to say the probability. He wants the probability that it's greater than 1 and all this stuff. To get that, what you have to do is look at the functional form of of his cosine thing, this thing up here, and forget omega t, forget that 100t. See where it's greater than 1. Promise you, you should be able to pound through that one, but I'll do it for you in class next time. That is a tougher problem. There's a lot of tricks to that one in this one, believe me. And the other one that's tricky, it's not that tricky. I mean, there's a lot of trickiness here, but is this one right here in 5-2. Here you got a train, and the thing is, get rid of any complexity. A commuter is arriving at 8 a.m., but he has a random variable between 7:55 and 8:05 is how he actually gets there. So it's really got a height of 1/10 from minus or plus to from minus 5 minutes to plus 5 minutes. Just think of it that way. Get rid of the 8 o'clock. Then the train leaves from 8 to 8:10, or it leaves from 0 to 10 minutes after. Still has a probability density of 1/10. All right, now this is a classic one. First, get the density functions. Then he wants the value z to be equal to, and he says x minus y. You can do it that way. Once you do that and you put it in terms of the distribution function, then take the derivative with respect to z, you're going to get the density function he gets. But take a real shot at working through these. I mean, really throw down on this. It's not easy. But if you can plug your way through this, not just look at the answers, but I mean, really try to get through it and understand, I think it's going to do you a world of good, because these are the problems that foul people up left and right on exams. And do all the section 3.5. I'll go through 3.6 and 3.7 you don't have to worry about, because that's the whatchamacallit, the characteristic function. We're going to do Laplace transforms.